This video is the solution to number 39 in chapter 34. The problem gives us a solenoid of diameter 2 centimeters, length 10 centimeters, turns of 100, and resistance of 0.1 ohms. Now the solenoid is in the middle of a 4 centimeter diameter ring, and we're asked to find the current in the loop at t equals half a second, t equals 1.5 seconds, and t equals 2.5 seconds. The current in the solenoid is shown in the graph to the right, and from this information we can go about solving the problem. Now, we know from Lenz's law that voltage equals negative d phi dt. Now, phi is just equal to the area times the B field times cosine of theta. And in this case, because we're getting maximum flux, cosine is just going to be 1. So, differentiating phi, we get that d phi dt is equal to dA dt times B plus dB dt times A. And in this case, since our area is not changing, that area, the dA dt term will turn to 0, which will cancel that. And because the magnetic field is also not changing, according to our graph, since the slope is 0 for at t equals 0.5 seconds, our magnetic field is also not changing. So d phi dt is equal to 0, which means our voltage is equal to 0, thus meaning our current is equal to 0. So for part A, I is equal to 0 amps. Now for part B, we're asked to find it at 1.5 seconds. Now, according to our graph, we have a slope now of negative 40 amps per second, and using the same equation from part A, we can find d phi dt. So in this equation, we have a dB dt. It is not a 0 term, but our dA dt still is because we're not changing the area of the solenoid, or we're not changing the area of where the magnetic field is. So dB dt, we can find that by plugging it into our equation for a solenoid, and using the information we have, we can find dB dt to be 0.0504 Tesla. Then we can find the area of the magnetic field, which is just going to be the area of the solenoid, because that's where our magnetic field is enclosed. So finding the area and finding dB dt, we multiply them together to find the voltage, which comes out to 1.58 times 10 to the negative fifth. And they give us the resistance at the beginning of the problem, so we used that information to find current, and I found it to be 160 microamps. And moving on to part C, where we find the current at 2.5 seconds, it's very, very synonymous to part A in that our current is not changing again. We have a slope of 0, so our magnetic field is not changing, our area is not changing, and that means our voltage is going to be 0 since our d phi dt is 0, which means our current will be 0. And that's the solution to this problem.